So we are the Innovative Digital and Smart Characterization Techniques Tools. Welcome to the session. I am Piotr Wojda. I work for the European Commission Joint Research Center. And I'm one of the chairs of this session. The other chairs are Erika von Zuben and Guido Paliaga. And they will be helping me to follow up on the presentations. I briefly introduce the subject. I think that now, especially at the digital age, these techniques and tools are becoming very important, also from the European Commission point of view. So, as you know, the European Green Deal is one of the big initiatives of the Commission. There is also the digital age, which has to be enhanced, let's say, with all its aspects in different programs. And in the zero pollution ambition for Europe, Commission is also calling for the use of digital tools and digital techniques for localization of pollution and contamination, and then characterization and following up. Also going to the remediation techniques and further monitoring. So I think that this session is in the heart of the European Green Deal. Also, of course, looking at the international aspects of this. So I'm already curious to hear all the presentations. Maybe some time to present you Guido and Erika. Guido, may you intervene, please?
Yes, welcome to everybody to this interesting session. I am Guido Paliaga from CNR. I work even as a consultant in the field of environmental geology in the last 21 years. And then I am a member of RemTech Expo from the beginning of this great adventure in the year 2007. So I've seen these conferences evolving, and I'm happy to welcome you here. And then please to Erika. Thank you.
Thank you, Guido. Erika.
Hello, everyone. I'm Erika von Zuben. I'm chemistry. I've been working for 22 years with environmental site assessment in Brazil. And since 2018, I'm also in this practice in Portugal as an environmental assessment head on a project team. And I'm a technical director of IESAS. And I'm honored to be joining you in a such important conference.
Thank you very much, Erika, for this introduction. So I think that we can go on with the session and come to the first presentation. Noemi will be presenting to us fact sheets on contaminated land and sites. She is project manager specialized in contaminated land and sites at the French BRGM, and she promotes the use of innovative technologies. So please, Noemi, the floor is yours.
Good afternoon, everybody. So I'm Noemi Duprat, the French Geological Survey. I work in the Contaminated Land and Site Department, and that has three main goals. The first one is to help public policies in contaminated land and site management. The second one is to assist private companies in technological development. And the last one is to make some research on innovative treatments or techniques. The management of contaminated sites often comes down to the chemical analysis of soils, water, or gas samples. But it's well known that chemical analysis of samples are not solely sufficient. And this is true not only for site assessment, but also for remediation works or environmental monitoring. Chemical analyses are well developed and give useful information on the contaminant presence, what and where it is, and on the overall quantity, how much there is. But we know that it's also necessary to consider additional parameters, such as the contaminant mobility, bioaccessibility, or the contaminant toxicity. And it's important to evaluate these parameters because they improve the relevance of the site conceptual model and hence lead to more robust and efficient remediation strategies. So many technologies have been developed and validated for several years to measure these additional parameters, and some of them are innovative. Some are innovative because they are newly developed, and some because they come from another technical field. It's the case, for instance, for the geophysics techniques or molecular biology tools. When they are applied to the contaminated land and site field, they can provide further information on chemical classical analysis. For instance, they can give the ecological state of the soil via the presence of microorganisms, which cannot be evaluated with only chemical analysis. Some of the techniques of geophysics allows duration reduction because they cover large areas. Moreover, if the appropriate techniques is chosen, it can improve the site conceptual model or lead to cost reductions. However, although they can bring a lot during the contaminated site development management, these innovative techniques are often insufficiently used. And the main reason of this in-use is that stakeholders are not well informed regarding the benefits they can provide. So in this context, the French Geological Survey, the BRGM, launched a project in 2019 on behalf of the French Ministry of the Environment, and in close collaboration with different experts from the French National Institute for Industrial Environment and Risk, the INERIS, and of the French Agency for Ecological Transition, which is the ADEME. The aim of this project is to share information about such innovative technologies in order to encourage their use. A wide range of stakeholders is targeted. It can be project owners, public sector bodies, project managers, administration, or service providers. The project aims at presenting a wide panel of innovative technologies that are believed to be relevant in the context of the contaminated site management. The users are informed on new but mature technologies, which can bring further information to classical chemical concentration assessments. All the given information intends to help product owners to understand the technology and guide specification, and allows product managers to justify the chosen technique towards administration services. To fulfill this goal, it has been decided to produce and diffuse what we call innovative fact sheets. So what is an innovative fact sheet? It has been sought to present the main feature of the technology along with practical information. Practical is really important. They are designed to provide keys for rapidly evaluate whether the technologies are adapted or not to the studied sites. In this way, they also help to choose between different available technology, depending on the contaminated site's context. One sheet is composed of a brief conceptual description and presents the context in which the technology can be applied. It indicates the contaminants that are relevant and the equipment that the user has to buy or to rent. In the second part, the methodology to follow is described and the technical limitation are specified. For instance, for the geophysical technology, they are not recommended in urban zone where there are a lot of magnetic interferences. The pros and cons of the technology are then summarized. For instance, the main advantage of dendrochemistry is to estimate the date of contamination of the period over which contamination was absorbed by the tree. However, the lack of commercial laboratories in France for the dendrochemistry analysis act as a barrier for a more widespread use of this technology. In the last section, measurement, times, and costs are proposed. It's necessary to know how much the technology will cost and how long it will take, at least for a standard study, to decide if the technology is suited to the stakes at hand. By this way, these sheets can help in the decision-making progress. Finally, they propose references for further information on the technology. This can be standards, successful research project, publication, presentation, etc. All the mentioned documents provide complementary details and help to get started with these innovative techniques. So here are some brief examples of these innovative techniques. The CSIA is the compound-specific isotope analysis, and I know there is another presentation about this technique a little bit later. It gives the relative abundance of two stable isotopes, which is noted as a delta, from which we can withdraw a lot of information about the contaminant. Indeed, it can help to discriminate two different sources of contamination, but it can also highlight the mechanism of the organic contaminant degradation. And it gives results in only one sampling campaign. This technique is consequently really useful during the site assessment. It can also be applied before initiating remediation works when it's necessary to check the feasibility of a remediation technology with the site conditions. Feasibility pilot trials must be led, and compound-specific isotopic analysis can inform on the contaminant state of degradation. With the isotopic result, it's possible to adapt or validate the chosen remediation technology. Unfortunately, the small number of laboratories with both isotopic and contaminated site expertise is the main drawback which prevents the widespread of this technology in France. Another example is the use of geostatistics. Geostatistics gathers several mathematical methods to understand and represent the contamination evolution in time and in space. It can be used during site assessment or remediation work. The main advantage of this method is to give the uncertainties associated to the contaminant map. It allows to adapt the sampling strategy in order to reduce uncertainties and thus to know our site better, which is of course the key of a successful remediation project. The association of geostatistics and field measurements is another great advantage because it gives information directly on site. We don't have to come back to the office to have the results, which is a good point once again during site assessment. To be efficient, this technique requires a lot of homogeneous and reliable data, at least 30, and must be led by an expert. That's why it's interesting to use it only on sites where there is strong issues. My last example is Bioaccessibility Test. Several laboratory methods exist to evaluate the human exposition associated to soil ingestion during the site assessment stage. It's really interesting technique that give keys to estimate the contaminant toxicity more accurately than chemical analysis, and thus to better evaluate the impact of the pollution on human beings. It is then possible to direct some different remediation strategies. Moreover, following the UBM method, detailed in standards, secure, robust results. The main disadvantages, it is only developed for 3 metals, which are arsenic, lead, and cadmium. And another drawback is that also some of these methods are available in standards, like the UBM test. Only few laboratories in France can do it, so the delays can be long. So far, 15 sheets are available. On the internet BRGM site, ssp.infotherm.brgm.fr, and 5 new sheets should be published within a month. New sheets are already considered for the next years to broaden the covered field. In November, we will also lead a feedback in order to evaluate the impact of the sheets on the contaminated sites field. This feedback will also let us know which information is the most useful for the stakeholders. Depending on the results, the sheets could be brought to change a little, perhaps to be more exhaustive or, on the contrary, more concise. And finally, the integration of the sheets in the French well-known decision support tool SelectDepol is being studied for the next 2 years. This integration will broaden the affected audience. And another advantage of this website is the online decision tool. Thanks to filters like the type of contaminant or the media where the pollution is, soil, water, gas, the stakeholder will be able to compare the technique in an easier way. So thank you for your attention, and I will be glad to answer your question at the end of the session. And don't hesitate if you have any remarks, and write at my email address. Thank you.
Thank you very much, Noemi, for this presentation. I really like this idea of fact sheets, and the one that interested me the most from your presentation is on geostatistics, because it's nice for the site assessment and remediation, and maybe also follow up when we want to know the long-term effects. So thank you for this. I will collect questions, if any. I will pass the floor to Guido, maybe to introduce the next speaker, please.
Okay, thank you, Piotr. Thank you, Noemi. Let's go to the next presentation. Title is Harnessing the Power of Big Data Sets to Optimize Bioremediation. The speaker will be Kate Clark, who is the technical director at Microbial Insights, where she supervises the daily scientific and technical operations of the lab and coordinating all the activities. Kate Clark received her BS in biology from Rhodes College and went on to complete her PhD in chemical engineering from the University of Tuzla. So the floor is yours, and let's see your presentation. Maybe it's arriving. Okay.
Okay, great. Can you see my presentation okay?
Yes, that's good.
Okay, thank you for that introduction. In my presentation today, I'll cover how large data sets have been used to synthesize microbial results with other lines of evidence in order to optimize biodegradation processes. So over the past several decades, our knowledge of biodegradation has grown exponentially. There's an increased understanding of the underlying processes involved, and thanks to the decreased cost and increased accessibility for sequencing, new biomarkers relevant to these processes are routinely being discovered. We can target these specific functional genes in microorganisms using quantitative polymerase chain reaction, or Qpcr. For also more widespread adoption of molecular biological tools like Qpcr, in addition to advances in high-throughput analytical methods such as quant-array and next-generation sequencing, has resulted in the generation of an abundance of microbial data. And although these sampling results are generally kept siloed by site, we believe that bringing together data sets from multiple projects can generate powerful insights that would benefit the field as a whole. So with all of the microbial data being produced, it's important to take steps to understand what all of that data means. So an ongoing challenge is to help site managers interpret their microbial results. In the literature, threshold concentrations have been established for some Qpcr assays. For example, a concentration of 10 to the 4 cells per milliliter of the helicoides is associated with generally useful rates of complete reductive dechlorination of chlorinated ethenes. Being able to correlate a concentration of a microorganism or gene with a degradation rate estimate would be very helpful to practitioners trying to establish time to closure. However, these types of studies require large data sets of microbial results across multiple sites. So in my talk today, first I'll provide a case study from a complex chlorinated solvent site where extensive groundwater characterization resulted in close to 39,000 data points. And I know that isn't realistic for most sites, so then I'll give a more accessible example of an internal laboratory database containing Qpcr results with over 20 years of field data that can be used to provide percentile rankings. And then in the final example, I'll describe a Department of Defense funded research that's performed to examine potential correlations between trichloroethene co-oxidation rates using a 14C TCE tracer method and Qpcr analysis of oxygenase genes encoding enzymes capable of co-oxidation of TCE. So I'll get right into my first example, where site managers used a large data set of contaminant, geochemical, and microbial results to establish site-specific operating parameters to optimize bioremediation efforts. The study site's been an industrial facility for more than 50 years. In 1969, a grass fire engulfed the drum storage area, destroying drums of waste byproduct from the manufacture of 1,2-dichloroethane. And this was a major contributor to historic groundwater contamination at the site. The groundwater is naturally saline with TDS around 8,000 milligrams per liter. So the site poses a number of challenges to remediation. First of all, there was residual DNAPL and very high contaminant concentrations in the groundwater. Historically, the parent compounds 1,12-TCA and 1,2-DCA were present at concentrations as high as 1,000 milligrams per liter. Chloroform is also present at concentrations up to about 30 milligrams per liter. And chloroform is a particularly potent inhibitor of reductive dechlorination of chlorinated ethenes, most notably vinyl chloride. There was also very high background sulfate concentrations, around 400 milligrams per liter. And then lastly, there were physical challenges. It was a large old source area covering about 7.5 acres. The dissolved plume is also large, extending about 2 kilometers off-site, where it's intercepted by a deep, leaky sewer. So the site managers performed extensive groundwater monitoring. They looked at contaminant concentrations and daughter products. Geochemical monitoring included volatile fatty acids, manganese, ferrous iron, sulfate, and dissolved gases. In terms of microbiological analyses, they did Qpcr and later quantarray as the number of gene targets of interest increased. So I've shown here a contour map of concentrations of the helicoides during an early site assessment. The helicoides concentrations were only greater than the 10 to the 4 cells per milliliter threshold recommended for generally effective rates of reductive dechlorination in areas of the source zone. Substantial populations were only detected in limited areas under sulfate-reducing conditions. Under the more mildly reducing conditions that were across most of the source area, the dechlorinating bacteria were detected at lower concentrations. So full-scale biosimulation was implemented, injecting propylene glycol as a donor. This was manufactured at the site, and so it was readily available. For many injections, what became known as biowater was used to help flush and distribute the propylene glycol. Biowater was on-site groundwater extracted from a pumping well that had a high dihelicoides concentration. So basically, it was a native bioaugmentation. So the impact of biostimulation was readily evident. Initially, dihelicoides concentrations only exceeded the 10 to the 4 threshold in the western edge, but following the propylene glycol injections, populations of dechlorinating bacteria increased substantially, resulting in enhanced anaerobic biodegradation of chlorinated compounds across the site. So at this point, the team had a rare opportunity. They had almost 300 samples spanning more than 2 years, with quantification of dechlorinating bacteria, accompanied by comprehensive characterization of contaminant concentrations, and a full spectrum of geochemical conditions. The different statistical approaches were used to identify the key operating variables, develop target concentrations for these parameters, and then to identify any factors that may be hindering biodegradation. The redundancy analysis indicated that out of the geochemical parameters that were routinely measured, volatile fatty acids and sulfate concentrations had the strongest correlations with dechlorinating bacteria. So here I've shown the results of one-way Anova, where the VFAs were the grouping variable and the log of various dechlorinating bacteria were the dependent variables. So taking a look at the plot, we see when total VFAs are below that 1,000 milligrams per liter, the DHC concentrations are typically below our minimum threshold level of 10 to the 4 cells per milliliter. So as a rule of thumb, at this site, we really wanted to be above 1,000 milligrams per liter total VFAs to ensure that dechlorinating bacteria were not limited by low electron donor availability. So we did the same thing for sulfate, which is a known competing electron acceptor. We can see here that in general, concentrations of all dechlorinating bacteria were lower with increasing sulfate concentrations. Concentrations of Dehelicocoides were significantly lower at sulfate concentrations greater than 50 milligrams per liter. Since chloroform is known to be such a strong inhibitor of reductive dechlorination, we also examined its impact. The one-way Anova was conducted with a subset of the data where growth was not limited by electron donor availability or sulfate concentrations. The Dehelicocoides concentrations on average were substantially greater than 10 to the 4 cells per milliliter when geochemical conditions were favorable and chloroform concentrations were less than 4 milligrams per liter. So from the statistical analysis, a set of site-specific operating parameters were established for VFAs and sulfates. Further analysis found that high total chlorinated compounds or salinity didn't adversely affect Dehelicocoides. However, chloroform concentrations greater than 4 milligrams per liter were inhibitory. And it was chloroform inhibition that seemed to be causing the low DHC, this former surface pond area, that large section of white. To overcome this, the site managers designed a groundwater recirculation system where fresh water was pumped from a non-source area well, injected at the upgradient edge, and then biowater with high Dehelicocoides concentration was extracted from 3 source area pumping wells and re-injected upgradient of the inhibited area. So did this approach work? Yes. Here's the Dehelicocoides contour map following that treatment. The Dehelicocoides concentrations now exceed the target concentration across almost all of the source area, including that formerly inhibited area. So I'd like to conclude by highlighting the overall impact of enhanced anaerobic bioremediation at the site. After the treatment, the estimated mass discharged through this transect decreased by 80%, and this level of reduction has been maintained for years now. So in terms of site management, the statistical analysis helped identify the most important parameters affecting the growth and activity of Dehelicocoides. The site managers adapted their remedial approaches based on the performance monitoring data. And as I mentioned at the start, one of the challenges you have with data from an unfamiliar analysis is to be able to put it into context and determine what the results mean for a site. So recognizing that many clients aren't as familiar with interpreting microbial data, an internal laboratory database was established to house Qpcr data, and an external client portal allows retrieval of percentile rankings of specific Qpcr results and start to connect subsurface microbiology to contaminant biodegradation and site management activities. The Qpcr database has over 25 years of data from census and quantity projects, including results from over 50,000 field samples from all 50 states and 42 countries. The database provides percentile rankings comparing a client's results to all the other samples we've tested for a particular assay and sample matrix. So we want to do that to give a broader context instead of just sample selection providing a site-specific perspective, which is very important. The Qpcr database provides a broader perspective where you can compare your results to sites around the world. So a client wouldn't need to have years of experience with Qpcr data to be able to say if it's a high, moderate, or low concentration. So we have these percentile rankings to help clients gain perspective on the results. If your results are at approximately the 86th percentile of all the samples we've analyzed, degradation is more likely than if your results fell in, say, the 35th percentile. So the final example is on research correlating Qpcr data and degradation rates. This study was part of an ESTCP project looking to support M&A with quantitative lines of evidence for abiotic degradation and co-metabolic oxidation of chlorinated ethanes. To assess the potential for chlorinated ethane co-metabolism, water samples were collected from 5 unique sites. We did Qpcr analysis, in addition to 14C TCE co-oxidation rate studies performed by Dr. David Friedman's lab at Clemson. We did 5 different Qpcr assays associated with aerobic co-metabolism of TCE on each of the samples. And then here's an example of the correlation between phenyl hydroxylase gene concentrations and rate constants derived from the 14C TCE microcosm studies. You can see here that a phenyl hydroxylase abundance in the 56th percentile correlates to a TCE half-life for around 7 years. So an average concentration of this gene, based on the Microbial Insights database, can still yield a relevant rate of co-metabolism in the field. The studies show that Qpcr is a good second line of evidence for screening for co-metabolism as a possible mechanism of degradation. Didn't have time today to show all the data, but Qpcr assays for PAG, RMO, and SMMO correlated well with the 14C TCE co-oxidation studies. So just in summary, at the chlorinated solvent site, the statistical analysis performed on that site-specific dataset was used to establish operating parameters to achieve effective reductive dechlorination. However, with limited time and funds, it's not often feasible to obtain a database that size for a single site. So site managers working with datasets, comparatively smaller datasets, can use tools like the Qpcr database to leverage multi-site datasets to draw stronger conclusions and help gain stakeholder acceptance of remedial action plans. In new research efforts to correlate degradation rates with Qpcr concentrations require samples from multiple sites in order to determine the utility and limitations of predicted rates. But this line of inquiry has the potential to improve the accuracy of current decision frameworks and site conceptual models. So that's the end of my presentation. Thank you for your time and attention today.
Thanks to you, Kate, for your very interesting presentation and for respecting times very, very well. I wish to invite the audience to write every questions on the chat, so we will be able to discuss in the final stage of our session. And then I leave the floor to Erica for the next presentation. The floor is yours.
Thanks, Guido. Thanks, Kate. Now we see one interesting case, soil sample, understanding assessment and its importance in the management of contaminated sites. Matheus Ewald is a geological engineer specialized in management of contaminated sites. He works at Finkler with a characterization and evaluation focus on alternative, high resolution and sustainable solution. So the floor is yours. Let's your presentation.
Thank you, Erica, for, can you hear me well?
Yes.
Okay,
perfect.
Great. Thank you for the introduction and good morning, good afternoon, everyone, wherever you are in the globe. I'm talking now from São Paulo, Brazil. And today we're going to discuss a little bit about uncertainty assessment when dealing with the management of contaminated sites and how soil sampling carries that uncertainty to very high standards, actually. Sampling, let me get a pointer here. The sampling phase is the base for every work in characterization and creation of a conceptual site model in a given site, right? But lithology is complex, and we must address it correctly in a way that we can create a conceptual site model that is robust, that is accurate, right? So we can move forward with the remediation in the best way possible. So our goal when managing a contaminated site is to reduce uncertainty. And in that way, we support a reliable decision-making. We can be sure what the options are there for us to move forward. And when talking about soil, that's where it gets tricky, because it's usually the smallest area at any given site, but it has 90 to 98% of the mass. That's what we found in our investigation, and that's what's in the literature. So the most part of the mass is in a very small area. And this mass in the soil creates all the other ones, like the vapor and the salt phase. So how do we address this soil? How do we address the factors? And what are the factors that carry uncertainty? And how do we address them? Understanding that soil is the biggest villain in a contaminated site. It's complex. It's not homogeneous at all. And we are going to see that in a minute. How do we move forward? How do we account for that uncertainty? So traditionally, traditional investigations start with sampling at any site. And when we start sampling in these point samples, we assume, we make two assumptions. One, that this medium is homogeneous, and two, that there is a linear spatial correlation between where we sample and the concentrations that we are finding. And that's not true, because the medium is complex, is not homogeneous at all. And the correlation between sampling locations is not linear. We cannot predict that. We cannot assume that. So how do we know that the samples we collected are representative of the contamination? Given this complexity, given the importance that the soil carries for the understanding of all the other phases and how we go and what is available there for the remediation phase. And I'm going to give a very simple example, because I think everyone's played this once or saw Minesweeper. It's a game where the idea is to find the bombs that are hidden in the board, right? But we never know where they are. So going sampling at a given site is like marking the bombs, just straight out of the gate. We're trying to find it. We may have a primary source area, potential source area, but that's horizontal. We have nothing on the vertical level at all. So we're going sampling and marking bombs just from the start. So that's the traditional investigation. It's based in multiple blind samples, and blind sampling campaigns is going back and forth to the field to sample more, to reduce that, to try to reduce that uncertainty. But with this whiteboard blank, how do we measure the uncertainty? How do I know I don't have anything anymore? How do we decrease that uncertainty? With more samples? Maybe. We could sample each square here in the board, but that's not feasible. It's not economical value. We cannot do that. It's too expensive. And the answer is innovation, dynamic working plans with real-time data collected on the field, high resolution in triad. I left a link in the presentation for my talk from last year, talking about that type of investigation. But we need real-time data to tell us where things are before we sample. And then we can measure how off we are from reality. So the case study that we ran, and we're still, it's still ongoing, we did 656 high-resolution log locations, mostly with MIP to see the VOCs, and OIP because we had the LNAPL potentially at the site. And what these logs gives us are clues to where things are. So we know where we have a 1, we have less chance to have something there. And we know areas that we don't need to sample at all, because all the indicators show us that there's nothing there. And we also, at the other end, have areas with 4s and 5s, like here. So we know there's a lot there, and then we need to sample. So from these log locations, we sample 156 verticals, or 20%-ish of the area, where we went and collected samples. And how do we collected them? We collected 602 in the whole area until today. And 57% were in areas where there were evidence for VOCs, because we are analyzing chemistry and lithology at the same time with the log, high resolution logs, right? But we need to sample more in these areas because there's more uncertainty. We are not sure if those signals are representative or not, and we need to sample. And this is the bigger area of any site. As I said in the beginning, most of the mass is in 10% of the area. So most of our samples were in areas with low detections, but we need to sample to reduce uncertainty. And 14% of the samples were in high concentration areas, where we had that evidence from before. It's the smallest area with the higher readings, and the most mass is located there. And we are going to see statistically these samples that we collected in these high areas, because with chemistry that we had the data from before in the lithology, we were sure that there were VOCs underground in the lithology. There were free NAPL. So what those samples that we collected tell us from the quality of the collection? So in 89% of the samples, we had measurable VOCs in the lab. We missed 11%. And these 11% were in areas. Here is a typical MIHPT log, right, from the site. And these samples were from these logs, these high readings here. So there's chemistry indicating that there are VOCs in there. We missed 11%. Why? How do we account for that? The three factors that I'm going to show you all are pretty obvious, but we were able to measure them and account for them. First one was depth. Up to 3 meters, so shallower points of collection, we got 93.5%. But we went below 10 meters, we were just 80. So as deep as you go, and these samples were collected with dual tube, right? So we knew which intervals we were. But below 10, it was pretty hard to get a sample that matched the chemistry that we read before. It's more challenging to get a proper soil sample, like 5 grams from 11 meters of soil cores, right? Then the water table. Below the water table, our accuracy was 79%. We didn't have VOCs in 21% of our samples that we knew we had VOCs in there. So the water is a challenge. And we were fortunate enough to run 2 crews, very experienced field crews, but the one that was slightly more had a better success rate in measuring that VOCs, having that sample collected properly in what we were seeing before. So it's quite interesting when we have that previous data showing us what we need to sample, we still miss it sometimes because of these 3 factors that we were able to find out. So just to finish here, takeaways on the traditional approach with uncertainties. We cannot answer the question, how hot is that spot? There's an article from 1992 questioning that. How do we know that the sample we collected is the highest in that area if we just collected like 5 samples? We cannot answer that. How do we assure that the samples that I collected without previous knowledge of a site are representative of what I want to see? One practice that is used is to screen for VOCs with a handheld PID, but different soils will release VOCs at different rates, different speeds. So there's different results. So there's no methodology to select those samples. So they cannot be used to do that. And point samples shouldn't be expected to tell the whole story of a site because they're not capable. They're just 5 grams in 2 tons of soil in 1 square meter. So we're selecting just a tiny bit of a whole area. How do we know? So therefore, if we go traditional approach, blinding samples, we cannot measure uncertainty. There's no methodology that will help us. And we cannot ensure the proper understanding of a contamination of this mass that will generate the mass flux that will create vapor intrusion. We won't be able to get the full spectrum. We can get tiny parts, but not the whole picture. And then when we have this qualitative evaluation of geochemistry and the physical medium, the lithology at the same time, we can target specific areas for sampling and even installing precise monitoring wells. Because we have this horizontal and vertical density of points, we can sweep a vast area in no time at all. We decrease our blind spots. We even can eliminate them by going back if needed, if we still have uncertainty in some area, because we're able to identify the hotspots, because we swipe the whole area. And then the sampling, it needs to be done after a dense qualitative or semi-quantitative evaluation. We need to have information about where we are collecting the samples beforehand, because if we open the core, we try to describe the lithology, the VOCs are gone. By the time I select the 5 grams from all of that, they are gone. We're not going to get anything. We, with all the data going for specific zones, we're still missed because of the depth, because of the water table and the crew experience. Sometimes we didn't get what we were expecting, but we need that before. So if we want to reduce uncertainty, to have a better management, to create a more robust, precise conceptual soil model, we need to evaluate the soil with the quality that it requires, because it's complex, it's hard. And we need this real-time data on the field, going dynamic. We don't have a matrix of points planned for an area. It's dynamic. We go one place, we go another, we see a signal. We do more in one area, we focus where we need to focus. So high resolution tried approach, dynamic working plans are the key to be even able to measure if our samples are good or not good at all. So that's the message that I want to leave with you today. And thank you.
Thank you very much, Mateus, for this interesting presentation and examples. So there might be some questions at the end of the session through the chat. Let's go to the next presentation presented by Tom Hatton. It's 4 easy steps to large building vapor intrusion mitigation. Tom has over 30 years of experience in design and installation management of radon and vapor intrusion mitigation systems, and he's also founder and CEO of the Clean Vapor company. Tom, the floor is yours. I think you're muted for the time being. You are still muted.
Clicking on it. How about
yes,
now?
It works.
Oh, good. Go back to the beginning then.
We still don't see your presentation, so
yeah, I'm trying to bring it up.
Good.
How about now?
Not yet. There's no screen being shared.
Clicking the shared screen.
Have you found back the button of share screen, the green one?
Yeah, that's what I'm clicking on.
Uh-huh.
I don't know why it's not coming up. It did when we tried it.
Yes, we tried it, and now there are some troubles.
How about now?
Not yet.
Don't see it now?
Actually, I don't see, no.
Oh. Why it's not sharing. You want to have somebody else go ahead of me and then I can go out of order?
Maybe, yeah. So we can change. I don't know.
It is Marco speaking. Go ahead with another speakers. Tom, please shut down Zoom and reconnect with Zoom. Maybe could be some problems that we can solve. I will make you co-host again. Okay, Tom? Okay.
So I hope that the next speaker, Wayne Jones, is ready. It's on groundwater spatiotemporal data analysis tool. So Wayne or Luke Rock. It's from Shell. So this presentation was skipped. Is that right, Marco?
Yes, you are right, Piotr. Hope they could join us next year, but this year it was not possible.
Okay. So we skip to the next. We'll see the environmental digital twin. I think that the digital twin is becoming more and more popular. Also, okay. So Calvin, you are ready with the presentation?
Yes, of course. I can start here.
So we can share your screen and then please.
Can you see correctly?
Yes, we can see clearly the presentation, full screen.
Thank you. Let's go. First of all, guys, it's a great pleasure to be here in Rentec, be part of that. Great presentation until now. Very happy to see some friends here, Erica, Mateus. So my name is Calvin Yost. I am the technical leader of the digital data management sector at Citrel. And my first message here is I'd like to share on personal perception of the environmental market is changing quickly in the last few years. I think it's a similar movement as the banking and telecommunication sectors years ago in direction of digital revolution. So in this movement, we can see some keywords appearing each day in our market. For example, digital innovation, data acquisition, data analysis, data processing, data visualization, user experience, each more normal in our projects. But we miss a general concept, some kind of method to understand all the relations between the multiple expertise areas that bring all together and create this new culture to all stakeholders. In same direction, we noted that some new standards was created before using some general terms, for example, conceptual site model, high resolution. And when these concepts were created, we see some kind of revolution in our market. After some in-depth overview observation of contamination projects that show us that on one hand, we spend lots of time studying environmental components, and it's good. For example, water level, lithology, geochemistry. And on the other hand, we spend very few time observing the building assets, buildings, pipelines, tanks, in equipments that directly causes the source of contaminations. We believe that a correct conduction of the environmental projects should consider these built assets and the environmental aspects. We only solve the contamination problem when we track and solve the issues with our built assets. So I would like to say hello to environmental digital twin. In this next slide, Before talking about the environmental part of this new concept, I would like to introduce what is the usual digital twin approach. The main aspects of a digital twin is to be a virtual representation of something. A building, equipment, a room, a tool, a process, something. This digital twin tries to mimic or simulate the constructive aspects, the geometries, the layers, and the process and mechanisms, how this thing works in the real world. Actually, the digital twins works very well with Internet of Things, IoT, and consequently with real-time data. And also this technology use methods and technologies like building information model, and actually we can use machine learning and predictive analysis over this information. In this slide, I would like to describe how the environmental part can be used in the context of digital twin. I would like to describe the concept, the general concept of environmental digital twin. We define that like virtual representation of build assets and environmental liabilities that brings real-time field information for fast decision-making and reduce exposure to environmental risks. Behind this, we have to consider several things. For example, for environmental, we use a lot high resolution. So this digital twin application must support high resolution data. As we know, to reduce the uncertainties of conceptual site models, we frequently use high resolution techniques to get better assumptions. High resolution techniques can be observed from different perspectives. For example, above ground, we can use UAV, drones, etc. The most common techniques for high resolutions for underground, for example, membrane interface probes, MIPs, geophysics, etc., is another perspective. And finally, we have to consider the time-related aspects of high resolution. For cases when we have to have a better overview of measurement across time, vapor intrusion, for example, and for that, we generally use IoT and telemetry. Other key aspects of environmental digital twin is have to have a user-friendly representation. This is one of the main aspects of digital twin, and this can bring the complex language of environmental sciences to a easy-to-understand approach, making possible to multiple different backgrounds users get insights from this product. Another aspect is big data. The environmental digital twin needs to handle well with big data. As mentioned before, big data and high resolution works together. Databases with millions and millions of registers are each day more common in our environmental daily activities. Some very well-known environmental cases easily surpass 5 to 10 million analytical results registers in their databases. And in the end, GIS and BIM, the integration between concepts of GIS and BIM are key aspects for this environmental digital twin success. As you know, guys, GIS is a gold tool for environmental analysis, used in our market for a long time with several cases of success. BIM is not so new, but this technology ability to manage and structure data from building assets and guarantee the collaboration of different professionals during the life cycle of these environmental projects. It's a different method to work. It's not a tool, it's a method. With focus in building assets, geometries, costs, planning, maintenance, execution, and operation. Business intelligence concepts and tools are also a hot aspect in this approach. The business intelligence put all the things together. In this slide, you can see in the left side a famous approach for conceptual site models. Probably you see this before in a lots of reports. With this in mind, I would like to introduce to environmental digital twin proof of concept in this slide. Here you can see a simple concept of what we are proposing to market to use this environmental digital twin approach. All the information in this model is hypothetical. We are using mock data. So all you are seeing here, guys, is not real. It's just a proof of concept. You can access this model, this interactive model. You can access and click and drag all the things using this QR code in the left side. Feel free to use anytime. And here we can see some key aspects for this example. For example, here we can represent in a digital interactive representation of a whole industrial unit, some communities and some assets to be protected, like rivers, lakes, soil, groundwater, etc. We can see here to the contamination mass, some information about that. Concentrations over time for our wells, lithologies and well constructions, plumes and geographic information, and IoT and sensors, all together in the same screen. As you can notice, this is a broad concept. With this discussion, I would like to make some investigation to our market. Why our environmental reports couldn't be more digital and friendly? Why not? Who is responsible to digitalize our market? The governments, the consultancies, the site owners. Once Mahatma Gandhi once said, you must be the change you wish to see in the world. So we believe we are the responsibles to change our market in several aspects, including digital part. But I comprehend some of you can say that do not have the background, the expertise, the digital approach enough to move toward these digital projects. In my opinion, everyone can help to achieve this goal, to digitalize our market. If you know nothing about some technologies, you can write tutorials about these digital products. You can add a translation to a specific product. You can add some examples, show how to use these products. You can answer questions for others, helping disseminating this knowledge. You can offer to mentor another contributor or developer of these digital products. So finally, I would like to introduce ourselves, our team, our company. We are a digital and data management sector of Cetrel. Cetrel is one of the biggest 100% Brazilian environmental engineering, industrial, and consultant companies. Besides the consultant part, Cetrel is responsible for Camaçari industrial environmental management in Bahia, Brazil, and waste and water treatment of these sites. And after that, the water distribution too. My presentation is very short. I would like to thank for our audience, guys. Feel free to contact me in LinkedIn and ask a question about this section. Thank you, guys.
Thank you very much, Calvin. A very interesting presentation, especially when you were presenting different elements of the environmental digital twin, high resolution visualization and big data and geointelligence. There are some aspects that are of interest for me, especially also the visualization, how to create dashboard or easy access. So thanks for this. I will try to get back to Tom. I don't know if Tom hears us. Tom?
Can you see my screen?
No. when you try to push the green button, share the screen, can you select one of your screens or options or applications?
What about now?
There's something coming on? Yes,
Okay.
there is a PowerPoint with the presentation.
Now, you got it?
No, full screen, full screen.
Oh, excellent. Thank you for your patience. I really
No worries.
appreciate it with this technical issue here. Thank you so much. My name is Tom Hatton. I have a presentation of 4 easy steps to efficient vapor intrusion mitigation. I've been in the vapor intrusion mitigation business since 1985 and spent most of that time remediating about 11,000 sites and developing new innovative technologies. The most important purpose of a vapor intrusion mitigation system is to be protective of people. That's to stop the vapors from coming up from the soil into the building and affecting people. What is a vapor intrusion mitigation system? What is vapor intrusion? It's the upward migration of soil gases into buildings. Most of the things that we work with are PCE, TCE, carbon tet. We work some with petroleum hydrocarbons, benzene, diesel. We do some work with inorganics, hydrogen sulfide, a lot of work with methane, and also naturally occurring radon. Most vapor intrusion comes from your source contaminators, your industrial sites, which you see on the left in the graphic, gas stations, dry cleaners, breaks in sewer pipes, and other various things that discharge chemicals into the soil that float along on the groundwater until they encounter a low pressure that's induced by a home or a building. Those chemicals are drawn in, and hence you have a vapor intrusion problem. The basic form of correcting vapor intrusion is to depressurize the slab, and that's what this talk is going to be about, mostly is soil depressurization systems. They need to create a negative pressure below the slab. They need to run continuously, and they need to achieve some level of performance as dictated by usually a regulator or a client. That's to create, in most cases, a minimum pressure differential below the slab. That's the difference in pressure from the soil below the slab and into the building of at least 1 Pascal at the outer extent of the negative pressure field under adverse conditions. These systems require quarterly inspections so we can make sure that they're running correctly. There's also reporting requirements to both clients and regulators, and the use of telemetrics and new technology has made this advance much better. So we want to properly characterize the site. This is something that Matthias just talked about, the importance of doing this correctly and having the data of the soil lithology, the groundwater, the contaminants, the direction of flow. But most importantly, where are the contaminants below the slab that you want to depressurize them and defining them correctly. This here is a building where they first developed flat screen technology, and before that it was used for orchard products. So it had a variety of things below the slab, chillers, foam floors, and things that made it very complex. There were 18 different slab areas, and when the TV company moved out, a government-funded solar panel manufacturer came in, and they wanted all of every molecule of contamination under some type of engineering control. And we said that there was thresholds or soil gas concentrations that had to be met before we went and depressurized the soil. We spent about 3 days with a mobile lab characterizing and taking mobile lab samples below the slab and deciding which areas had to be mitigated and which did not. The area that you see in the green, we were able to eliminate from the mitigation area and save the client approximately $145,000 US on mitigating these properties. I also knew where the hot spots were. So when we designed the mitigation system, and that's in the stippled area, we were able to target all the areas that needed to be depressurized with precision amounts of vacuum. And the post-mitigation sampling indicated that we had hit non-detect for most of the building and below thresholds of standards everywhere. Once you know the area that's defined that you're going to work in the building, you're going to characterize the building, catalog all the cracks, the openings, all the areas where vapor can come into a building. You're also going to look at what are the pressure differentials that induce vapor intrusion, that cause that low pressure in the building that you have to overcome. The slide in the lower right-hand side, this was a building that was a quality assurance lab for wire polymers. And with all the fume hoods on in this lab, it created a inside negative pressure of 2¼ inches or 560 pascals, which means that I had to design my system, or if you're designing a system, you have to overcome the natural pressures that are inside those buildings, both the convective ones from the building and also any mechanical devices that depressurize buildings. The next part of it is you need to understand the soil below the slab and the permeability of that soil below the slab to properly design the system, because you want to know how much vacuum you need to apply, where it needs to be applied, whether it's a high vacuum, low flow blower or high flow, low vacuum. This building built aircraft cables from about the end of World War II into the mid-2000s. They started out their business in unit number 1. You can see that right there. And what we do is we create little wells below the slab, and we take out some soil, and then we drill 1/4-inch holes on an X and Y axis. And you can see those lines there. And then we apply different quantities of vacuum to those holes, and we measure the extent of vacuum on how far it goes below the slab, down to an accuracy of 10,000ths of an inch water column or 1/4 pascal. And we also measure the airflow that's discharged from that pilot blower device, because when you're sizing a blower, it's a combination of how much vacuum does it need to apply, and then what is the airflow. Blowers operate on a curve, so you want to find the sweet spot of that blower. But what we found in this exercise in this building was the area that's in red there, that took 16 suction points in an 8-horsepower direct drive radial blower, while the other unit 2A there took 2 suction points and a 200-watt blower, because that soil was very permeable. And the different colors in these zones indicate different zones of permeability, which enable you to make a design that's specific for the building and matches the soil permeability, so you can maintain the vacuum fields that you need to meet the requirements of a functioning system. Once all the field data is gathered, you want to go in and do a design. You want to keep in account that soil permeability, the airflow yields. If it's a little bit of airflow yield, you're going to have a smaller diameter pipe, and you can put more pipes on more riser pipes and suction points to draw on the soil on one blower. You want to look at the HVAC system, and you may have to compensate for that, such as in that polymer lab. You want to verify the building materials that you're going to use are going to meet the requirements of wherever you're building. Some places it's okay to use PVC, other places it's not okay because of fire housing, and most buildings have a designated use group that you can match to. One of your other largest considerations is how much reserve capacity should be inside the motor. Now, the difference in temperature between inside the building and outside the building is the largest driver in vapor intrusion. So a system that you may design for Portugal, the Catalan region of Spain, or Sicily is going to be very different in its excess motor capacity from something that may be designed in Finland, Norway, or Sweden. So there's various different types of motors that you're going to use for different regions depending on the temperature swings of that area. You want to pick the right motor. There's a lot of different blower motors, and there seems to be maybe a little bit less in the UE than the United States, but you want to have a motor that will properly depressurize the soil. A lot of SVE engineers want to use SVE motors. They're very good for depressurizing soils where there's very low airflow and high vacuum, but they're not very good for vapor intrusion mitigation systems. In those cases, your radial blowers, your three-phase radial blowers are going to work out because they have a much more gentle motor curve, or high-speed compact radial blowers where you can run them in RPMs that may range from 1200 RPM all the way up to 15,000 RPMs, and you can create a lot of vacuum with a very small motor, like you see there in that lower right-hand picture. Next comes the build part. That's kind of the part that's very important, where you have people who worked on the diagnostics, worked on the design, they understand the build. Take a little step sideways here for new construction. I happen to like new construction a lot because you can design things using the right size stone, the thickness of the stone bed. You can design your pipe diameters, your vapor barrier to have a very effective plenum below the slab and passive venting. And you can also integrate the telemetry at that time so you can know what those pressure differentials are. And when you're designing a system this way, if you do it right, it will not require a motor and it will vent itself just fine passively. The next part of this 4 pillars is the remote monitoring and management part. It's the part that I'm very interested in because a lot of times these systems get installed and after the consultant gets paid, they kind of forget about it, but the people in the building still need to be occupied and protected. So what the remote management part does, it tells you that the system is working. It provides a record of what's going on day to day and hour to hour. And what it does is it tells you that you're protecting the occupants of that building, and it also protects the owners from long-term liability from vapor intrusion risk from people who may want to litigate because they receive some type of cancer. Now, there's also ways to control these things by varying the speed of the motor. And I talked about excess capacity within the motors in an earlier slide. When air wraps around a building and the colder that air gets, the more convection it creates within that building. So a system that seems to work fine in the summertime, if you're in a varying climate region, may not work at all in the winter time because you may not have the vacuum fields that you need to stop vapor intrusion. Here's a graph of a constant motor speed, which runs at 2,700 RPM. The outside temperature is on the red line. The subslab pressure differential between the soil and the building is on the blue line. And when I developed the telemetry here, it became very clear that temperature was the main driving force for vapor intrusion, and that we had to develop controls that would stabilize those pressure differentials to make sure that at no point vapors were getting into the buildings. So we put together a pressure differential system and this monitoring and management system, which is taking off well in the US right now, where there's a sensor below the slab. It senses the difference in pressure, and the computer runs the speed of the motor. So you'll have a constant amount of vacuum applied to the entire slab. And normally you would put this at the outer extent of the negative pressure field, so you could always maintain your 1 or 2 Pascal goal from that system. And just to recap here, the 4 steps for vapor intrusion mitigation are: first, you want to do your diagnostic part, and you want to understand what's going on in terms of your contaminant, how it's getting into the building through vapor intrusion pathways. You want to diagnose things through a proper soil permeability mapping, understanding the pressure zones of the building. You want to go out and build it. And then the last step is you want to put into some type of remote management plan that will make sure that the system will run far into the future. And I'm giving a talk on the remote monitoring and management part on Thursday. So which we're going to go into the last few slides, and we're going to expand that out to the full 15 minutes. So I want to thank you very much for first being patient about my internet connection. And secondly, I want to thank you for listening to this presentation. And we'll be in the vapor pin booth. If you want to come by, if you're here live and ask questions, we'll be there for the next 2 days. Also send me an email at thatton@cleanvapor.com. So thank you very much.
Thank you very much, Tom, for the interesting presentation, especially what caught my eye was passive mitigation measures in building and also adverse weather conditions that have to be taken into account. Thank you very much. And I will pass the floor to Guido to introduce the next speaker.
Okay, well, thank you, Piotr. Let's move to our last presentation of this very interesting session. Well, the next presentation will be from Paul Hatzinger from SERDPE-STCP. The title of the presentation is Application of Stable Isotope Analysis for Assessing the Environmental Fate of Insensitive Munitions. Paul Hatzinger is an environmental scientist with more than 25 years of experience evaluating the fate of emerging contaminants. He holds a PhD from Cornell University and has been the principal investigator of more than 30 research grants focused on pollutant source identification and remediation. So the floor is yours, Paul. And
great, thank you, Guido. Can everybody see my screen?
Yes.
Okay,
yes, yes.
Fantastic. So today I'm going to discuss the application of stable isotope analysis to look at the fate of insensitive munitions. And I'd like to also introduce my sort of co-people on this talk, which are Neil Sturcio, Linnea Harati, and Chunlei Wang at University of Delaware, and then Mark Fuller at Aptum Federal Services. And a lot of this work is Chunlei's PhD research. So by way of background, insensitive munitions are replacing traditional explosives and formulations primarily due to safety considerations. So in particular, DNAN on the lower left is replacing TNT. So we're seeing TNT move out of a lot of these different formulations. And 3-nitro-1,2,4-triazole 5,1 is replacing traditional RDX. So this compound NTO is replacing RDX in many formulations, and these compounds are much more shock sensitive than TNT and RDX, and thus it's much safer for troop handling and in case you have fires and other things, you get less explosions that are not intended. So in terms of the environmental fates of these, well, they require investigation. These are relatively new compounds in the environment, so we need to know how long they persist. What are the most common mechanisms of degradation? And then also, how can degradation be documented under field conditions? So as these compounds become introduced on ranges and in other military environments, how can we then determine if they're degrading and by which mechanisms they're degrading? So that's where we're looking at compound-specific stable isotope analysis, or CSAA, which you heard introduced in the first talk today. And the scope of this project was to develop and validate analytical methods for DNAN and NTO, and that's CSIA methods, and then to determine carbon and nitrogen fractionation during degradation, which I'll explain in a little bit. And some of the different processes that we've taken a look at include photodegradation, biodegradation, alkaline hydrolysis, and then mineral reduction. And I'll show you a subset of those data today. And I'll also mention that this project, you can look for more details under the CERTUP organization, which is a research organization of the Department of Defense, EPA, and DOE in the US, and its project number ER2726. And on my last slide, I have a link if you're interested in more information on this project. So by way of background, so CSAA is actually the analysis of isotope ratios, and in this case, stable isotope ratios. For example, N15 to N14 in different molecules. Typically, it's conducted by GC, isotope ratio mass spectrometry, so you need volatile compounds. And it's basically reported as per mil or part per thousand differences from a set standard. And I'll explain that a little bit further. But why is this useful in the environmental field? It's useful because isotopic ratios often shift, and they usually increase in a predictable pattern as a chemical degrades either biotically or abiotically. And this is known as the kinetic isotope effect. So if we look at my little graphic here, these are bacteria biodegrading RDX, and we see different isotopomers with either light nitrogen or heavy nitrogen. And what tends to happen is that chemical biodegrades. So we get an enrichment, so we get a higher ratio of N15 to N14, and also we see decreasing concentrations. And we get an isotopic depletion in the first product. The reason this happens is the bond strength of an N15 RDX is slightly greater than that of an N14 RDX, so the degradation rate of this is slightly quicker. So this enrichment can be used as very clear evidence of degradation, and it can be even more powerful if you can measure more than one isotope, for instance, both carbon and nitrogen in RDX. Now, when we plot this type of fractionation out, what we often do is look at natural log of F. So this is the fraction of the original compound remaining. So in this direction, we have a declining concentration from right to left. And then this is, again, a log plot often of the ratio of, in this case, N15 to N14 in the compound as a function of time over that original ratio. So what we often get is a linear slope here, and the slope itself is actually called a fractionation factor, an epsilon value. And this is, by looking at these epsilon values, you can tell the extent to which you get fractionation of these different elements and molecules. And you can use this then to determine A, whether something is degrading, and also B, sometimes what mechanism of degradation is occurring. So just one slide on some of the methods here. There were some methods developed for DNAN. Those were improved at University of Delaware, and essentially you have to separate that material from everything else that's in your sample. And then basically it gets combusted to carbon dioxide and nitrogen. The isotopes of carbon are measured in carbon dioxide, and isotopes of nitrogen in nitrogen gas. By IRMS, and then you calculate those different ratios in your samples. The nice thing is there's not a lot of compound required, so it's only about 150 nanograms to do carbon isotope analysis, at about 1.5 micrograms for nitrogen analysis. NTO is a little more complex. You can't just analyze NTO straight. So again, University of Delaware and Chun-Lei Wang in particular looked at a lot of different derivatization methods and ended up with a means by which she could actually methylate the NTO, making it more volatile and more readily separated from other compounds in solution. And then you could measure carbon and nitrogen isotopes. And again, not a lot of materials necessary, about 800 nanograms. Okay, so starting with DNAN, and I'll talk primarily about DNAN today with a little bit about NTO at the end, because there's a lot of NTO work still ongoing. But the most common biodegradation pathway for DNAN is a nitro reduction. So either of these two nitro groups gets biologically reduced to an amino group, and you end up with either 2 amino or 4 amino nitroanisole. And then there's, pathways that go further to break this down. But usually in CSIA, this first step is actually the most important step in determining the fractionation of the different elements that you're looking at. Okay, so here's an example. This is an organism, Pseudomonas Fluorescens IC. It contains a variety of different enzymes, including some oxygen-insensitive nitroreductases that can reduce DNAN. Interestingly, this organism can do that under either oxic or anoxic conditions. Thus, the oxygen-sensitive nature of some of these. But that's important because that means DNAN, even though this is a reductive process, can degrade under aerobic conditions. And we see here, a control, and then this is biodegradation by this organism under different conditions, anoxic, heavily oxic, or just under room air. And you can see, degradation of the compound in all three cases. Now, if we look at the fractionation of nitrogen and carbon, and this is similar to the plot I showed before. So in this case, DNAN is biodegrading. So less is there. And this is again, the fractionation. So this is parts per thousand difference over time. So essentially this molecule is getting heavier, it's getting more enriched in N15 as a function of degradation. And the epsilon value here is about -15, -15.4. So that's a very strong fractionation. That's something you can certainly see in field samples. And that's a nitrogen-oxygen bond that's actually being affected. So it makes a lot of sense that nitrogen in particular would be heavily fractionated. You don't see nearly as much carbon fractionation, and notice that these y-axis are about 10-fold different. So although the slopes look similar, this is almost, this is significantly less at about 2 per mil. And then if we look at the ratio of these, which also can be very useful in determining mechanisms, it's about, -7.7. So, you should be able to readily detect isotopically DNAN biodegradation in field samples based upon this fractionation and assuming this is the pathway that's being taken. So we took a second look at this, and we were doing some work to seed a biological reactor that's being developed to treat a mixture of explosives. And we were trying to develop a seed culture that would degrade many different things. And these are sort of kegs that we were using to do that. But in this case, we don't know what organisms are here. We're sort of taking a look at that right now. It's a mixed culture, but we see it degrades DNAN. And again, you see those aminos developing, a little bit of 4-amino, which disappears, and then 2-amino nitroanisole, which then slowly biodegrades. So we took samples from this, and this is a complex matrix with a lot of different explosives and fermentation products of cheese whey and many different organisms. So this is a nice example of trying to separate your compound in a complex matrix. And the results that we saw were very similar to the Pseudomonas in that you had a very strong nitrogen fractionation. You had much less carbon fractionation. And again, that ratio was on the order of, in this case, 7.2, but very close to what we saw with the pure culture. So again, that's a good sign. It suggests a similar mechanism in this batch. And it also shows you that you can separate out the DNAN for isotope analysis from a very complex matrix. And then one last example, this is another set of samples, and this is some soils and runoff that came actually from a live fire range, so a military range in the United States. We're taking a look at what type of explosives run off from these environments. But we added some glucose and fatty acids to some of this sample, and then fed it DNAN as an electron acceptor and or sole nitrogen source. And basically in this range enrichment culture, we again see biodegradation of DNAN. So samples were collected along the way, isotopic analysis was conducted, and we see again a very similar pattern. So strong nitrogen fractionation, much less carbon fractionation. And in fact, the carbon data here aren't particularly good. You see the fit is not particularly good. And as a result, this fractionation factor ratio, so the ratio of essentially this slope to this slope, is a bit higher than we saw for the pure culture or we saw for the batch reactor. Now, essentially, I think this is basically because of the data set. But the other possibility would be that there's a slightly different set of enzymes or slightly different mechanism of reduction occurring here. And that's sometimes what you need to look for if these ratios vary quite significantly. But I suspect in this case, it probably just has to do with this data set. But from an overall perspective, it again shows this pattern of very high nitrogen and relatively low carbon fractionation during biodegradation. The next set of studies were photolysis, and these compounds not only degrade biologically, the sun can degrade them over time. In this case, the study was run in a reactor, so this is a UV reactor. You can use different wavelengths of UV light, And the system was set up so that there was a batch of water with DNAN. It was pumped through the reactor and recycled into these containers. And there were multiple studies going on at once. And this is done for a period of days. And then you look at degradation of the compounds. And you can set the wavelength. In this case, we're looking at UVA, or about 350 nanometers as the wavelength. And what we see is degradation of DNAN, photolytic degradation, with the production of dinitrophenol as a key product. Now, this pathway is can be very complex, and there's a paper cited at the end of this if you're interested in photochemistry. But in a simple manner, the DNAN seems to go through a state of photoexcitation, where it then can undergo a nucleophilic substitution per DNP, or at least this seems to be, one simple explanation for how this is degrading photolytically. But there's photoactivators, nitrate can play a role in this. So this can be very, very complex in terms of interpretation. Now, the isotope fractionation during this process was really interesting. We won't worry so much about DNP, but there was a typical carbon enrichment in DNAN. So as DNAN degraded photolytically, you see isotopically an enrichment in the carbon isotopes, so C13 to C12. But very interestingly, when you look at nitrogen, in fact, there's an isotopic depletion. And this is pretty unusual. It has been seen in some other photocatalytic processes, but essentially what's happening here is that the N15 is reacting more quickly than the N14 DNAN. So as DNAN degrades, you're actually getting isotopically depleted. So, this is a positive slope rather than a negative slope. So the neat thing is, this is very characteristic for photolysis. You're almost never going to see this in a biodegradation or a mineral reduction process. So the interpretation of this is this has potentially to do with the photoexcitation, where 14 DNAN undergoes this more readily and maybe cycles back and forth. And I'll just let me bounce backwards just for a second. So it seems to have to do with this step in the process. N14 maybe gets excited and relaxed and sort of goes through this, whereas N15 DNAN is either in this state for a much shorter period of time or just gets directly substituted to DNP. So therefore, the N15 reacts more quickly in this case. So you get this positive slope, or basically an isotopic depletion in nitrogen. And just sort of the last process, we looked at alkaline hydrolysis. Many different explosives, including DNAN, are subject to alkaline hydrolysis. This is sort of the general process. You again end up with DNP, but again, by a different mechanism than either photolysis or biodegradation. And the isotopic fractionation. So again, these epsilon values, and this looks curved because this is not log transformed. But essentially what we see in this case is there's more carbon fractionation. So approximately -6 per mil for carbon and about -3 per mil for nitrogen. So that's a very different pattern than we saw for either photolysis or biodegradation of DNAN. So, importantly, I think what this shows you is that you can use this technique not only to document that this is degrading, but you can infer mechanism based upon the extensive fractionation, whether this is a hydrolytic mechanism, a biodegradation mechanism, or a photolytic mechanism based upon these patterns of carbon and nitrogen fractionation. Again, you really need both isotopes, but you can infer what mechanism may be occurring in the field. And this is the same for many different compounds. So, I would encourage you guys to, if you're looking at the fate of compounds, to consider this technique. So I'm going to finish up with just a few slides on NTO. And as I mentioned at the beginning, there was a lot of work done at Delaware just to try and be able to analyze nitrogen and carbon isotopes in NTO. So the project's a little further behind in terms of having actual isotope data. Took much longer to get the method developed. But essentially, when we look biologically at NTO, again, we have a nitro group. It goes through an intermediate HTO and then gets reduced to this compound called ATO, which again is the amino. And we've run some of the degradation studies. In this case, I showed you the batch reactor earlier. This was in that same batch reactor. So we also had DNAN in here and RDX, but we see these organisms degrading NTO. You see a little bit of production of HTO, this intermediate, and then pretty much a stoichiometric production of ATO. So we're getting the conversion here. We're doing the isotope analysis on this currently. And then this was that Pseudomonas Fluorescens organism. And the thing that was interesting here, if you remember DNAN, this compound degraded DNAN, whether there was oxygen or no oxygen present. In this case, oxygen inhibits degradation of NTO. So that suggests maybe there's a different enzyme involved. Maybe it's an oxygen sensitive process rather than an oxygen insensitive one. And it also maybe speaks to the fate of NTO in the environment, where you might see aerobic degradation of DNAN through these insensitive reductases, oxygen insensitive. Maybe you don't see that for NTO. So there will be a paper coming out, I'm sure, within the next year that'll cover this, but I don't have any CSIA data to show you for these, but I thought I would just kind of show some of the experiments in process. But we do have a bit of data for photolysis. Again, this is the same system I talked about before. In this case, you see NTO is photolytically degrading, and you see a bit of production of ATO, just like we did. So again, there seems to be some pathway where the sun excites this molecule, you get a photoactivated state, and in this case, you get some type of nitro reduction process down to ATO. We do have some isotopic data for this experiment, and everything is on one graph in this case, but what we see, if you remember previously with DNAN, we saw this reverse fractionation of nitrogen. So essentially it was going down with time. Here, this is reversed. So again, we have a typical fractionation of nitrogen in NTO, epsilon value of about -7.6 per mil. So what that means is that, you know, you have typically the N14 NTO is reacting more quickly than N15, as one would imagine. You really don't see any carbon fractionation at all. So the process has very little impact on carbon. But again, just based upon this, you should be able to see loss of NTO by this increasing ratio of nitrogen, although it would be nice to have a carbon effect as well. But the other thing I'll point out again is this fractionation is very, very different than what you saw for DNAN in terms of these patterns, which suggests, even though, you know, what I showed was sort of the simplified mechanism with a photoexcited state, you know, this molecule, the N15 and N14, clearly, you know, there's some very complex chemistry that's occurring for both of these compounds photolytically. So I'll just finish with that and just summarize, you know, precise and accurate methods have been developed for both carbon and nitrogen in DNAN and NTO, although NTO requires a derivatization. Stable isotope fractionation by bacteria, UV light and hydrolysis result in very different fractionation factors and patterns. And this should allow DNAN degradation to be documented in the field. And carbon and nitrogen fractionation of NTO via biodegradation is underway. And photolysis shows significant nitrogen, but not carbon fractionation. So just for further information, here are some papers that have been published out of this project, as well as a link to the website where you can look more. And we'd like to thank the CERTIP organization for funding this research. And I'll close with that. Thank you very much.
Thanks to you, Paul, for your presentation. And now we can hope that the floor for questions for the debate. So I leave the floor to Piotr to begin this part of the session.
Thank you very much, Guido. Yes, in fact, there are some questions to different speakers. Maybe we can start with the first presentation. So, Noemi, you were mentioning the fact sheet on geostatistics, and you were mentioning the site assessment, then the remediation work. Is geostatistics also used for the follow-up? So the monitoring after the remediation, just to be sure that remediation was, let's say, done until the very end, and we know that we remediated 100% of the problem. So let's say outside of the remediation process, in the follow-up process.
Yes, I think I'm not the expert in geostatistics, but I think it can also be used during the follow-up. You can use some samples and to actualize the map and to know the uncertainty. And I think also we can use it during the excavated earth, for instance, and you can use it with real-time sampling, real-time measurement on site, and so you can have the right concentration during the remediation and the following up.
Okay, I see. And also maybe in this process, I see the monitoring, which is very important, the monitoring network that could be also automatized to help, let's say, geostatistics. And I see also some connections with what Mateusz presented in his presentation. Okay, thank you very much, Nani. Maybe the second question to the second speaker, Kate. You were mentioning the use of Qpcr database. This Qpcr database, is it available? I'm not the specialist in the domain, so how you integrated this database and in the processes, Qpcr.
Sure, yes. So it is available to our clients. So if someone sends us samples for Qpcr analysis, when we send out the report, we also send a link to the database so they can log in and enter some geochemistry and contaminant data, so we can get some metadata going along with those results, and then they can see how their results compare to all the other samples we've analyzed for that particular Qpcr assay. So it's kind of limited access, but it's available to our clients.
I see. Okay, thank you very much for this information.
Thank you.
And okay, I will just go on with the third question and then maybe go to Guido. But first, Mateusz, there's a question from the public. Do you know about some tools that are available to select samples for inorganic analysis? So a screening, how to select the samples.
So in organic, there is not a probe like MIHPT or OIHPT you've used, because it's more complex to analyze them. But exactly. What we, luckily, metals or inorganics don't move that much, or they don't become vapor. So we have more time to work with the soil. So what we are doing, our approach is to use a XRF, X-ray, like a handheld X-ray gun, to screen our lighteners that we collect from the field. We don't do that in the field because the humidity of the soil, the humidity of the air, they interfere with the XRF. So we bring all the soil to our lab. We can dry the samples and then do a dense screening with the handheld XRF gun. And then we select the sampling. So I think for inorganics, that's, at least by what I've experienced so far, it's the best way to do it. It's the way we have been using with great success.
Okay, thank you very much for this additional explanation. It was a bit more technical question in the distinction between organic and inorganic ones. Thanks. Maybe Guido, you would have some questions to the speakers.
Yes, thank you. I would like to make a question to Calvin. I guess he's okay, he's hearing. Yes, here you are. Yeah. Hello. Your presentation was very interesting and very full of passion and of, I mean, communicating. And well, I'm interested in what is your opinion about the economic dimension of the perspective you have spoken about? I mean, both from the side of, I mean, communicating and so on, and from the technical point of view. What is your vision?
Perfect, Guido. Thank you for your feedback and your question. Yes, there is a great point of view of some managers, some directors that think that digital aspects, digital products could be expensive for their general environmental projects to the point to make that unviable, not possible to deliver with that scope. My point of view and my expertise about this topic is that the most consultancies that make the digital aspects as a key core product for his products can have new business, new consultants, new projects coming from this vision. You can, for example, offer to your client a new perspective in terms of structure their data, show their data, and communicate this data to other stakeholders, not that common ones, that governmental agencies and etc. So in a first approach, yes, I consider this as a challenge to convince our clients, to convince our stakeholders to adopting this approach. But with little moves, we can show the value of this approach and communicate very better. And in my perspective, this is very well received by all the publics.
So thank you. I agree with you. I think that this is a very valuable tool, and I think it will be developing in the future. Probably one of the possible future, business for such a kind of approach. I agree with you totally. Thank you. Thank you. So, Piotr?
Yes, I still have a couple of questions. Also to Tom, I have already mentioned that I was interested by this passive mitigation measures and adverse weather conditions. For the weather conditions, is it really influencing a lot
yes.
your methodology, or it's a, let's say, negligible factor?
Now, sometimes, depending on the climate zone, like if we were to take the difference between maybe southern Italy and up around Finland or Norway, to create the same pressure differential in the building may take 5 times as much electrical power in terms of what the motor size has to be. And because climate varies and temperature varies throughout the year, you don't want the motor running at a maximum speed to create that 1 or 2 pascals at the outer extent of the negative pressure field. So in buildings where we have varying climates in the US and in the northern part of the country, we can save clients usually over $1,000 US dollars in power cost between running the motors. So we're just using the energy that we need. So you get to extend your extended stewardship program, and you don't have to have as much money in the mitigation reserve because you're paying for it out of electrical savings. So it's very critical that this is done. And in the building where I showed the fume hoods from the polymer lab, the difference between a still night in August and a blustery day in January is 96% power difference to create the same pressure differential. So it's very important. And then on the new construction side, if you figure out your matrices for the stone, the void space, the diameter of the pipe, you look at the building geometry, prevailing winds, and my background is physics, so I apply those things to a design. And in 35 years of doing this, we've not had to put a motor on a building. So it works if you apply the math.
I see. So that's the link to the passive mitigation measures.
Yes, yes.
As well.
But you can't do passive in an existing building. It will have some effect, but you won't get the result you're looking for.
Okay, thank you very much, Tom, for explaining. Maybe last question to Paul, because you were speaking about munition, and I was wondering, I work with soil, and sometimes soil is degraded in different parts of Europe. I just look at Europe. And for example, Western Balkans are heavily touched by wars and existing munition. Do you have your case studies in different parts of the world? So do you have some statistics on maybe correlations between place, weather, and the methods and tools that you are applying?
Yeah, good question. For the topic I discussed today, for DNAN and NTO, you're not really seeing these in the environment so much yet. So these are the sort of the replacement compounds. So I would expect in the Balkans and throughout most of the ranges of the US, what you're really looking at there are RDX, HMX, TNT, perchlorate as an oxidant, right? However, these methods are applicable for all of those compounds. So there are isotope methods developed for all of those different compounds. Now, in terms of trying to understand, I think part of your question is trying to understand the extent to which some of these things are degrading in these different soils over time. I don't think anyone's really looked at that. There's a lot of work going on so the CERTUP ESTCP program, which I'm here representing today, is sort of the major funder in the United States of research in lots of areas, environmental areas, but particularly in explosives, transport, and degradation. So, there's quite a bit of information on ways to enhance degradation of these. There's bacteria break down all of these. So there's a lot of good information about how you enhance that. There's good information there on isotope fractionation of RDX, of perchlorate, of TNT. That's all done. In terms of a broader correlation of sort of, using these methods to determine whether you're getting, say, a lot more photolytic or hydrolytic degradation or biodegradation in some areas than others, I don't think that's ever been done. That would be a large effort. Samples collected around the world, and then maybe that's where some of your mega data analysis would be interesting. But I don't think it's been done
big data
yet.
Analytics.
You need data to.
Yeah.
To use big data, but I think we need the data first. Yeah,
of course. Thanks.
Thank you for the question,
Paul, for this. I don't know if Guido or Erica, do you have some questions left?
Not from me.
Or
Piotr, I have one question, and
yes, please, Marco.
It's as is near to the end. Is a very stupid question to Paul again, because. I would be interested in, Paul, that we had some problems here in former Yugoslav Republic with uranium, depleted uranium bullets left there. So my question could be, is it possible, as we are speaking about sustainability, that those concepts would apply also to army, and in case, forgive me the stupid formulation, we have a sustainable bullet that it will kill you, but in the let's say in the soil will biodegrade in, I don't know, 5 or 10 years, I don't know, whatever.
Yeah. So is your question, is it possible to develop sustainable bullets, or is it? That's
yes. The question is do you see this possible? And I wouldn't ask if Department of Defense is working on this, because I don't know, it's something that is not revealed in a common, let's say, in a common workshop like this, no?
Yeah, well, I guess that I'll give you a couple of thoughts there. The U.S. Department of Defense was actually looking at green bullets at one time, and I believe they were made of tungsten. And that also, then you get into this issue of tungsten toxicity. So I don't know how far that actually went, Marco, in terms of in terms of widespread application. But on the other hand, I've seen some projects where one of the biggest concerns I think around the world is also unexploded ordnance. So it's things that get buried, and even from World War II, there's still active munitions. So one of the projects that people were looking at was ways that you could formulate some of these munitions so that over time they would decay. Either the casing would decay, or to no longer make it an explosion hazard. So people do think about that, and even within the military, they think about trying to be more sustainable when these things get left behind. And so then some, civilians obviously are going to be exposed not only to contamination, but also potentially to an explosion hazard or something like that. So I think within the military, there are people, probably 40 years ago that didn't think about this, but today they certainly do. And in terms of new formulations, the caveat being that whatever you do environmentally to make this safer can't impact the performance of the munition on the military side. They're very concerned on the military side that, I've seen patents where people are talking about, putting, you could put something in that potentially hydrolyzes some of the explosives if it didn't explode over time, that sort of thing. So, but it's a great question and a big problem worldwide. And there are people who are thinking about it.
Thank you very much, Paul. I have, if I may, Piotr and Guido, you are the head now, and I would have another question for Noemi, if possible. I don't know the time.
Yes, we are a bit out of schedule, but still 2 minutes left.
Okay, yeah, we have those 5 minutes more. Now we can also disclose to the other. Noemi, I was not able to see your presentation because I was on the other side, with the STM. My question would be, but however, I'm aware of the great effort of those, let's say, guidelines or fact sheets of using innovative way to characterize. And it's very, very important that this BRGM, strong and very respected, also not only in France, institution that released them, together with ADEME and INERIS. I don't know if the spelling is correct, but however, my question would be, which could be the next development of those, that activity? You are working on other 4 or 5 documents with new additional techniques.
Yes, for this year we have worked on isotopic on metals, but also on the geostatistics with real-time measurements from the XRF, yes, in English it should be XRF, for metal measurement in situ, and also for speciation, which is really important to know the mobility and the toxicity of contaminants. And we could work on bioassay to know also for toxicity. And we want to work on different measurements for water. For instance, different depth measurement to know where the water comes from and the flow, and also for volumetric measurement to know for organic compounds. Yeah, we have a lot of ideas.
Thank you, Noemi. We have you will have sufficient material to come back next year for more news about your experiments with ADEME, INERIS, and BRGM together. Thank you very much. Floor again.